Okay, everybody, welcome to session 9 in Mechanics and Materials. Are there any questions before we get going, or comments? I enjoyed getting to interact a little bit over the GroupMe about our assignment with finite element analysis, and from what I could tell, yes, there was some messing around and trying to get things to work and frustration. And from also what I could tell, there was kind of some success. So I hope that we have the opportunity to do more of these examples, more problems where we get to show that what we're doing analytically matches what we're doing in simulation. And thus, we have some confidence in our answers. There is a in-class assignment that should have just dropped, and I also really appreciated your feedback over the weekend for the survey that we put out. So I'm going to attempt to do some things that seem to be in line with what people were requesting. Of course, some people are like, yeah. Some people are like, eh, right? And so we have to try to accommodate the majority. And so I'll see what I can do. Please feel free to send me feedback, and we'll probably have some more surveys that preserve people's anonymity in the future as well. Okay. Any thoughts, questions, comments? Okay. So today we're going to be talking about torsion again. Okay. So this is torsion 2. It's really like torsion 1.25 because we didn't really get a chance to hit torsion last time, and we will get a chance to review what we covered at the very end of the session. And we will, before we get into it, we'll have kind of a brief recap on session 8. We will have also some formulas and techniques. For normal loading. Okay. And what I'll say, I guess, is that the first part here, we're just kind of going to do kind of some information sharing, and then we'll get into from the past, and then we'll get into more kind of instructional sharing as we hit torsion. So kind of by the end of today, all right, I hope these are the things that we should be able to do. Okay. So we should be able to know something about the angle of twist. For a shaft. Okay, so how many radians does it, how many degrees, how much does it twist when we apply torque to it? We should know something about the maximum shear strain. Near the outer surface for a twisting shaft. We should also know something about shear strain within a twisting shaft. And we should have an idea about shear stress at the outer surface of a shaft, and also some of the shear stress within the shaft. So these are the things that we should be able to kind of cover today. Now, in the questions or in the survey, one of the things that people wanted to get a better handle on are lists of equations, all right? So now stop, well, you can copy what I just wrote, okay? But stop copying for a few minutes, and these are available for you, okay, both in the PowerPoint, okay, and in the OneNote link, and then they will be uploaded as a PDF as well, all right? But these are some of the relationships that we've talked about, okay? So we've discussed Hooke's law, all right, in terms of F equals K delta, in terms of sigma equals E epsilon. We've talked about stress in a bar. We've talked about strain in a bar. Okay? We've discussed displacement due to internal loading. We've discussed a general equation, plea, all right, for the displacement. At the end of a bar, we've discussed constants for springs, okay, in terms of their properties being a material property, E, A, and L. Okay, area, cross-sectional area, length. We've discussed thermal strain. We've discussed dilatation, all right, volumetric strain. We've discussed the relationship between dilatation and pressure related through the bulk modulus. Okay? So these are some of the big equations. Oh, yes. And then we also have these material property relationships with the Poisson ratio. Okay? So these are some of the kind of, it's not maybe the all-inclusive list, but from these basic equations, I think you could get to most of the relationships that we need. Using and manipulating them, that's the big puzzle, and that's the big question, right? Techniques for normal loading, okay? We have our three pillars. We have equilibrium, geometry or compatibility, or geometric compatibility, and we have constitutive equations. So what I just listed was pretty much relevant to the constitutive equations that we've been discussing. With equilibrium, first we want to do external equilibrium, and we use second law. Then we move to internal equilibrium, and then we use second law, or if it happens to be a truss, which does have normal loading in its members, in its two force members, then you could use method of joints, or you could use method of sections. And for geometric compatibility, often we're looking at, okay, what is the displacement of A relative to B? What is the displacement of B relative to C? And then can we add those to each other and say that's going to be the displacement between A and C? And then kind of related to using geometric compatibility is our opportunity to use method of forces, use superposition. Okay? So that on one page is kind of the overview of what I think we've covered with normal and axial loading. Okay? And so before the exam, which is going to be in about 10 days, probably want to come up with a backside, right? That's going to cover what we're going to discuss with shear and torsion. Any questions, comments on that? Okay. So, as a kind of brief recap from our last session, we discussed distributed axial loading, for example, with gravity acting downward on it. Again, don't copy this. This is just informational, and it's all there, okay? Because this is review. We discussed thermal stress. And please take a look. I updated example 8.5, all right? Now example 8.5 takes into account both thermal strain and force-based strain within the individual members, okay, to be able to calculate the overall strain or the actual strain in each of the members, not just the strain due to force, okay? What happens is we need to take into account how much expansion does each of these members have, and then think about, okay, that's the amount of strain or that's the amount of delta due to the heating. And then when we apply the force, think about how much strain, how much compressive strain, or how much compressive displacement we have. And then we actually need to add those to each other. Okay? And then we did finite element analysis, as we discussed. All right. So let's get back today. So today we are going to cover things like angle of twist, maximum shear strain within the twisting shaft, okay, and also shear stress in and at the outer surface and also within the shaft. So first, let's go back and look at shear, okay? Let's just talk about the shearing of a material element. So if we, draw our little cube that disappeared. Oh. Okay, we have something that looks like this. And in the past, we've kind of, drawn the different stresses on the different faces. Let's just say that we have, this is the x direction, and this is the y direction here, okay? And for now, we're going to take a 2D profile, all right? So we're going to do a little 2D profile, and just write out our element as a square. Right now, this has no stresses, no shear stress, right? No shear stress. No normal stress. It's just blah. And if we want to apply a shear stress to this, there's going to be some strain. Or if we have a shear strain, there's going to be some associated shear stress. Okay? So if we take what we have here and we just say, okay, I am applying some type of shear to this element. That's the y, that's the x. And the displacement here, this delta, by which I've sheared, okay, is going to be relevant to the shear strain that we have, right? And what do we divide by? Well, we divide by the height, right? So then this distance right here, y, we'll call it. Okay. So that the shear strain, and we would write it kind of like in terms of x, y, okay, in these axes. That shear strain we can just say is going to be delta divided by y. Okay? Now, in order to get a shear strain, often, okay, I guess there's probably, I'm trying to think if there's a way you could apply thermal load to get, to get shear strain without any shear stress. I should know how to do this. There's got to be something where it has chirality and you heat it up and then it expands and then it twists, okay? But anyway, for most of the cases that we're looking at in this class, okay, what we're saying is that there's going to be some shear stress, and I'm just going to draw the 2D element again. And this is, not picturing the distortion. And do you all remember what the convention is? Not like where we get together, but what arrows should I be putting on this element? Okay, or let's start here. Which face would you consider, or where? Okay, so where's the positive x face? Let's start there. On the right. Okay, good. Okay, so let's start there. All right, so that would be tau x. Okay, and then it's got to be parallel, so I put it in the y direction. Okay, so that's going to be, that would be, the convention would be it's up. Okay, I'll use a different color just for fun. Okay, so that's kind of like the first face I would usually pick. In this case, I might actually pick the top though, because I can kind of see, I'm going to erase it, but, well, I don't have to erase it. I can kind of see that there's a shear stress or attraction vector that's causing that thing to deform. So the next one that I would write would be this one. And this one makes sense. These make sense, okay? They're facing each other. These heads are facing each other right there. When I say the heads, I mean this and this. They're facing each other. And for this to be in equilibrium, as we've discussed previously, I need additional shear stresses. Okay? And all those values are the same. They're all equal to tau xy, right? We discussed this back, I think, in session 2. Or no, session 3, I think, was stress and strain. So how do we relate these to each other? So that's the question here, is how do we relate tau and gamma to each other? Well, if you're in the plastic region for a material on a stress strain curve, then good luck, essentially, right? We talked about the linear elastic, perfectly plastic, or the linearly elastic, linearly plastic. Okay, so you could use maybe the slope, or you could use a constant. But when we talk about this, we're really interested in the linear regime. Okay, so in the linear regime, right, for the elastic regime, we are expecting a linear relationship. Okay. And what is that linear relationship? It's a constant. Okay, it's a constant. And so we can say that tau is equal to g gamma. This is the constant, okay? This right here is called the shear modulus. Now, people don't usually plot. Well, sometimes they do. That's not completely true, but we're usually used to seeing a stress strain curve for normal stresses, okay? But we can also plot one where we have tau on that axis and gamma on the x-axis, and we can put a stress strain curve on here that looks very similar to what we had when we were doing a normal stress versus a normal strain. And the slope, okay, is given by g. We can also have, that's not great, but you can also have a shear strength, as you might expect, and you could also have an ultimate shear strength as well. But for us, we're essentially saying that with two parameters, okay, the main two parameters are going to be your shear strength and your slope or shear modulus. Any questions on that? So, yeah, any questions? Yes.
What's the gamma supposed to?
Okay. What do you think? If you look back at this picture now, what do you think?
Oh, is it the
Okay, so gamma, gamma xy, right? This one right here. That's what you're asking about, right?
yeah.
Okay, this represents the angle in radians that you have of this shift. Okay, gamma, I should have written it in here, so fine. That angle in there is gamma. Okay. There. Good. Okay, so usually it's pretty small. For the types of systems that we're looking at, it's going to be small. Okay, but it's the ratio of this displacement. It's really tan. You know, if you want to be more precise, okay, fine, we can be a little more precise. It's really tan of gamma xy is equal to the delta over y. But because it's such a small angle, we just say it's gamma. Okay. Good. Good questions. So, they want a full screen on the notepad window. Okay, well, I'll try to zoom in a little bit more. Right now, with the way I've got everything, this is how we're trying to do things. I'll try to write big enough for everybody. If you want to go back and see things, just click on the link on the page, and if it's working, you should be able to continually refresh and see everything that's been written in this notebook. Okay? So it's kind of like going back in history, in real time, hopefully. Okay, so that's shear. Now let's talk about twisting of a rod. Okay? So here, there's some funny thing there. It disappears, and then it should. Okay, come back. So let's imagine that we have there it goes. A rod like this. And we'll say that we're applying some torque TZ. All right, so right hand rule, what does that look like? That looks like something like that. Okay? Or like this, if you want. Okay, it's all TZ. That's being applied to the end. Now, if I have a line going across the top, okay, and we call this A naught right here. And if this is no load, okay, and then what we do is we say, this is the new position, A1, like that. Okay. So we've now twisted the shaft like this. So, you know, if I've got a piece of paper, all right, something like this, you guys can do this. And you can see there's a line here, right? There's a line where it is, and then and then I take it, and then I twist it. I try to twist it. First, let me make it a little smaller so it's in my hands. Right? I twist, and I see that I apply the torque that way, okay, which is not really the right-hand rule. If you want, I can do it like this, and that's my left hand, so that doesn't work. But if I do like that, right-hand rule, right, it twists, and you see the line come down. And that's what we're discussing. That's what a little line right there. That's what we're discussing. Okay? So, this angle with the center okay, like that. This angle we can call, use this one, I guess. Or maybe use this one. Phi. Okay? That's phi at some distance L. Okay? So if we say has some distance L like that. Okay, some length L. Okay, so phi L, and you can see that it starts off small here at this point, right? So if this is 0, right? So if I go all the way over here, phi of 0 is equal to 0. Okay? It's a linear relationship. Phi okay, at L over 2 is going to be 1/2 is going to be 1/2 phi of L. Okay? It's a linear relationship that goes with distance away from the center, or from the start, from the wall. And we can think of these as being stacks of disks. Okay, so if we have our shaft, right? Well, we can think of each one of these as, or one of these, the shaft as having a bunch of disks in it, like that. Okay, these are disks, or I like to think of them as pizzas. And I think if you look in the notes that I uploaded, I think yes, I did, of course. I was hungry when I was doing this yesterday. So I took, there's the disc, all right? Or here's our shaft that we're discussing here. And here is the table in the office, and there's a piece of pizza, okay? And there's the pizza right here. Okay? So you have that angle at different spots. So if we take one of these discs, let's take a disc. Okay, that's our disc. And we have our torque coming out like so. Or we'll say that's the positive z direction, all right? And then we have a torque, we'll say, following the right-hand rule on this side, we'll call that Tz, okay? And then that means that there has to be another torque going the opposite direction, that's equal, right, TZ. Like that. Okay, so that's just on one disk. Right, this is the same as what we did when we were setting up a bar and we have normal loading across that bar, right? If I take a slice, I have a normal load coming out of one side and I have a normal load coming out of the other side. Okay. And here, so essentially what we're saying is that the sum of these moments needs to be equal to 0 in the z direction. That's all. So, we've got a disk, we've got a piece of pizza. Let's do a little deeper dive into what's happening with that piece of pizza. And we'll say it's a deep dish pizza. So we'll call this trying to figure out shear strain on a torsionally loaded disk. Okay, and I don't know, you all can correct me in terms of, is it disk, D-I-S-C, or D-I-S-K? All right, I think they're pretty similar here. So if we take our piece of deep dish pizza and we draw it like this, and we have the no load on it, right? So this is the no load case. Let's look at kind of not the crust, all right, of the piece of the deep dish pizza, but we're going to look at some part of, I don't know, the cheesy section, okay? And what we'll say is that we have internally that looks really bad. Something that's doing. So this is B here, and this is C here. Okay, so B is at the bottom of the pizza, and C is at the top of the pizza. Okay. Now there's no load on it yet. Now let's put a load, okay, on this pizza. Okay. So let's draw it again, and now we're going to say yeah, okay, thank you. That we've got a torque coming out in the z direction and a torque coming out in the other direction, out the bottom, okay? And C was on the top and B was on the bottom, all right? So now, if we look at what's not happening on the crust, okay, there has actually, if we go back to this, if we go back to what we just drew here, you see this piece of pizza inside, okay? And you see this line, you see this gradation. So the bottom, if the bottom is back this direction, okay, over here, and the top is closer to me, facing me, you see that the top is going to twist more than the bottom. Okay, right? Because if I look at phi, and I look at phi at x plus dx versus at 5x, okay, at x plus dx, there's going to be more phi. There's going to be more twist. So here, if this is at some section taken from that shaft, B, maybe it was over here originally. So B naught was over here. Now B1 is over here. Okay? And it's shifted amount phi. And similarly, C naught was over here. And now this C naught has shifted, but it's actually shifted a little bit more. So we could call this C naught prime, right, if they shifted the same amount, and then we can call this C1. Okay. This is because the material has been twisted in this element. This is some element with height delta z. Okay? So let's take a look at what's happening here. If there's some twist in here, what does this begin to look like? And imagine there was another point and another point over here and another point. Let's just say there was another point over here and another point over here, another point over here, right? What are we starting to see? We're starting to see that there is some angle of twist. Okay, that actually should be careful. That's not the angle of twist. There's some angle associated with the shear strain, okay, in that piece of pizza. Okay. Questions on this? I know my drawings are not the best. Yes?
The base is fixed here, right?
So the base is not, okay? It's not fixed because this is I'm glad you asked that question. This is a disc, maybe it's this disc right here, okay? So this disc, right, is some distance away from the wall. And so the bottom piece has shifted and the top of the piece has also shifted, but the top of the piece has shifted a little bit more. All right, is that cool? So this twist, okay, is related to the angle of twist. Okay, so I should say that again. This shear strain, this gamma that we're seeing, it's related to the angle of twist, to the phi, all right? So what we're actually saying here is that in this region right here, on the top, there's some phi, okay? Let me zoom in. Try that again. Up here, and we could do it's phi plus delta z, whatever we want to say, okay? But that's the angle of twist. Yes, that's the angle of twist, okay, at that location. Now look, what do these two share in common? They share this right there, okay? So this highlighted length, okay, this highlighted length is equal to, well, what do you all think? I think I need to give you one more parameter, the distance from the center, right? So if I know the distance, this has a radius rho, okay? Let's see how I can do that. Yeah, I can do that. Actually, that's not that bad. We'll do it like this. This has radius rho, okay? No, the in-class assignment is not supposed to be one attempt only. If it is, then I'll go back and I'll fix it after class. Thank you. Okay. Have other people confirmed that? Okay. It's not supposed to be one attempt only. Okay. Sorry. I'll fix that afterward. I did have that thought of doing that, but I didn't want to do it in the end. Okay. All right. So, okay. So this is the rho. So that length ends up being rho, okay, times phi. Or it's really a d phi, okay, if you will. All right, and this we can call this a dz, if you will. So that length is a rho d phi. Well, I know what the height is, right? It's dz. So then I can define gamma, right? So we can call shear strain gamma is going to be, right, this distance. So it's going to be the rho d phi over dz. And that's how we define shear strain. Okay, so we should maybe distinguish these two from each other, right? So angle of twist, right, is phi, and that's something that we take if we're looking at the shaft as it's coming out, right, and we look at an angle, right, on the shaft. So that, you know, this is shaft, right? This is the pizza. That's the angle of the pizza. That's phi. Okay. This shear strain is something more subtle. It's the change in angle between corresponding pieces on the pizza. Okay? So like, you know, if you had a pepperoni on the top and you had, I don't know, a pepperoni on the bottom, bad analogy, right? You had some weird pizza, right? The pepperoni is at the same spot on the top and the bottom, but then the pepperoni shifts, right? Or we twist everything, and that pepperoni on the top just goes a little bit more than the pepperoni on the bottom. And that angle at which we have the shift that takes into account, right, the tangent of what the horizontal displacement is and what the vertical displacement is, at least the way we've drawn it here, that is going to be the shear strain. Okay. Great. Now, shear strain, what we see here, right? So we have shear strain So what do we see? It is proportional to rho. Okay, that makes sense. Okay, so what does that mean? That means that if rho is equal to the radius of your shaft, it's going to be at a max. Okay, and if rho is equal to 0, your shear strain is 0. Okay, so it's dependent on where you are relative to the center line of your shaft. Okay? The other thing we see is, well, yes, it's proportional to d phi dz. Okay? If we have the same internal torque, all right, And if we go back to our image here, okay, that I drew, that's kind of poor. Okay, I understand. Is the phi dz changing as a function of z? No, right? It stays the same. It's a line, right? It's a line, and it has a constant slope. As long as there's no interruption, as long as there's no torque coming into play in the system. So, another way that we sometimes write gamma, okay, is as follows. Okay, so sometimes it's useful. Let's see, is it going to do this weird thing it's been doing? I don't know. Sometimes it is useful to write shear strain as gamma is equal to a ratio of rho over c times a max strain. Okay, so what is this? C is the radius, okay, to surface, I guess you could say. Rho is, radius to selected point. And gamma max is, well, the maximum, right? This maximum, which is going to be at the surface. So max shear strain at surface. Any questions on that? Yes.
This is when the length of the bar or rod is fixed, right? So we're talking about it at a fixed location. How far you are from the center of the circle represents how much of the maximum gamma is.
Yes. So, how do I put this? It's probably safe to think of it as a relative, okay? Because I can draw a system, right, like this, and as long as I say these are the torques, and I define this as my zero, right? I'll say this is my zero. It doesn't necessarily have to be attached to a wall, right? As long as I have a balance of torques. Okay? But yes, for most illustrative purposes, this is coming out of a wall, okay? And that this end is fixed. This side is going to be fixed, or this side's going to be fixed, and we're looking relative to a distance from that wall. Okay. Good. Okay. So let's do a quick example. Here, what we're going to say is we have an angle of rotation of 0.1 radians, okay, at the end of a shaft. What is the phi at L over 2? Okay, so that's first, right? Well, that we already kind of did this, right? We said that that phi of z was proportional to z. Okay, so thus we can say that phi of L over 2 is just going to be equal to 1/2 of phi of L, which is 1/2 times 0.1 radian which is going to be 0.05 radians. Okay, not too bad. Okay. Now here's another question though. Okay, now we say that the length. Let's say length of shaft is equal to 1 meter. What is the shear strain? Okay. At a distance from the center line, rho at z equals L over 2 and L, or z equals L. Anyone? What do you guys think? Without doing anything, what do you guys think? Or how would you approach this problem? How would you approach this problem? Sure. Maybe having a picture would be nice. Okay. Fine. So let's draw a picture. That's Z. Okay. And we have some angle here, phi at L, that's equal to, they told us, to 0.1, or I'm telling you it's 0.1 radians. Okay. And let's say that we're interested in phi over here, which we said, right? The phi at L over 2, okay, was 0.05 radians, right? We calculated it out. And now, what we're interested in is, what is the shear strain? So, if I have, if I have these two disks, okay, I'm interested in knowing what the shear strain. Okay, so let's say if it's twisting this way, I'm interested in knowing what's the shear strain. At a particular location. Now, we can go back and we can look at the pictures that we drew if we want, and we say, okay, this is the relationship for the shear strain, right? Oops. Okay, this is the shear strain in there. Or we can go back and just look at the equation. We have gamma is equal to rho d phi dz. Now, we said that the slope is constant, right? Slope is constant along the length of this system. So if the slope is constant, how would I figure it out? Okay, so let's write out that gamma is equal to rho d phi dz. So this is constant. How do I figure this out? What is this value? Yeah? No? Yes. Sure. So the angle is 0 at z equals 0, right? Okay, and we need the slope, right? And the angle is point or 0.1 radians at phi or at z equals L, right? And we know that L is 1 meter. Okay, so the slope is just going to be the angle at z equals L divided by the length, right? So this is going to be rho times phi of at L divided by L, okay? And that's going to equal, let's see, we have 0.1, yes. So this is going to be 0.1 divided by 1 meter, okay? So that's what gamma is. Is gamma different at L over 2? No, it's the same, right? Because the slope hasn't changed. So whether you're at z equals L over 2 or z equals L, they're both the same. Any questions on that? Let's move on now. And our goal here now is to relate applied torque. So right now we just know what shear stress is. Or I'm sorry, we know what shear strain is. Okay? And we've talked about, okay, you can relate it through a G, right? So if you know what G, what the material property is, then you could figure out what the shear stress is. Okay? But right now, gamma is not related. We haven't said anything about how to relate it to torque. We've just been doing geometry up to this point. Okay? So now our objective here is to relate. We want to relate how do we get gamma? Okay, so the question, how do we get this? Okay, let me try to, I think there's a, let me see if I can, whoops, not there. Okay, let's do it this way. Let's move this out for a second. Okay. Let's just plot what's going on. Okay. Let's say on this axis, this is phi. On this axis, this is z. Okay? And let's say that here, this is 0, 0. Okay? That's the point of where we're at the wall, okay, or where we're calling our start. And up here, we said that, let's say that we said that this is 0.1 radians. Okay, so that's on the phi axis. And here, this distance is 1 meter. Okay? What is d phi dz? Right? What's the slope of this line? That's what we're asking essentially. Okay? Right? And the slope, we can say, oh, well, I know what the value is here. I know what the value is here, right? So I do rise over run. Okay? So rise over run. We'll have 0.1 radians divided by 1 meter. Okay? And so that is how we're calculating out, right? The gamma is equal to rho d phi dz. Okay, does that make more sense? Hopefully? Okay. Thank you for asking the question. All right, so let's keep going. We want to relate gamma and tau to torque. Okay. So, what do we do? Sure. You're welcome. De nada. I don't know how you say that in Italian. Anyone, how do you say you're welcome in Italian? Well, we are. Okay, well, all right. So let's start here. Let's remember that we have a relationship between strain and maximum strain. Okay? It's saying if you know what the max strain is, I can say, and I know where I am, and I know my radius, I can figure out what the strain is at a given location. Okay? So that's fine. Now let's also say, right, we have a linear elastic okay, or we're in that region, okay? So we have Hooke's law that says that tau is equal to G gamma. What does this mean? This means that we can now say that tau, okay, is going to follow this same relationship, right? What are we saying? We're saying, hey, this gamma over here, I could say that's like tau over G. This gamma over here, I could say this is tau over G. The G's knock each other out, and so just like the maximum shear strain was a max at the outside, the maximum shear stress is also going to be a max at the outside. Okay. Now, this is interesting in that we have a torque, or we have a shear stress acting over an area. Okay. You get where we're going here. Shear stress acting over an area, which means that if we integrate that shear stress over the area, we can come out to what the torque is. Okay? So, here we go. A picture. There's our circle. Let's say this is some internal part of the shaft. Okay? Let's say that this has some torque acting on it. We'll say that the torque, call that TZ there. We'll call it TZ there, like such. And let's take a little element and a little area element, and we'll say this is a dA. C is the radius. C is the radius. Okay, so in this case, C is the radius. Okay, so we're some distance rho to this element dA, and now we say we have a shear stress acting on that surface that we'll call tau. Okay. And what do we say? We said that tau, okay, according to this equation right here, if rho is equal to 0, then tau is equal to 0. But when rho is equal to C, when it's at the outside, it's at a max. Okay? So what we actually have on the surface is a distribution of shear stresses. Okay? So these are the shear stresses tau of rho. And they're increasing as they get away from the middle. So in order to come up with a relationship between these shear stresses and the torque, all right, what do? We say Tz is going to be the integral of all the shear stresses on the element, or on the face, okay, that we've selected, all right? So it's going to be tau but what is tau dA? Is it a torque or is it a little bitty bit of force? It's actually a little bitty bit of force, right? So what we're saying is we have our tau dAs, okay, and these are little dFs, and we need to multiply by radius, okay, in order to get to torques. Okay, so what we write is that this expression will give us the torques. Now, we have an expression right here for tau. Okay, it says that tau is equal to rho over c times tau max. So now we can write out rho tau. We can say rho squared over c, okay, times tau max, okay, dA. And this means that we can say that if tau max is a constant, we can write out that tau max times integral of rho squared dA is equal to this torque, okay? But what is the integral of rho squared dA? Oh, I forgot the c. We can't forget the c. Okay. The c. So what is rho squared dA? Well, this is something that we call the polar moment of inertia, and I'll describe this in a second in more detail, all right? But this is polar moment of inertia, and this is called J. All right? So then, in the end, what we write on this side is tau max J over C. And we can rearrange things such that, remember this is Tz, we can say that tau max is equal to Tz C over J. Okay, and this formula is one you want to remember. This is called the torsion formula. All right, but we haven't defined what J is. We'll get to that in just a second. Okay, any questions on this derivation? There must be some questions. So with this equation, we now have a way of relating to the torque that's being applied internally on a shaft to the maximum shear stress. And in New Jersey, I often refer to this equation as the TC&J equation. Okay, so our friends down at TC&J, all right, they have a leg up on us in terms of how to remember this. Okay, it's TC over J is equal to tau max. Or another equation, all right, so let's just, another way to write this, okay, if you don't necessarily want the max, okay, you can also write that just tau is equal to T rho over J. Yes?
Rho is just a number, but it's not like an expression.
It is an expression. Rho is the distance from the center line. Where's my mouse? Okay. So you see this is the center line or center point, right, on this circle, which is the center line going through the shaft. Rho is the distance from that center line, right? So here's rho, and that's the element we're interested in, potentially. Okay.
Oh, so it's not just like the radius.
Well, no. See, this is an interesting. Okay, so you'll find different terms, right, in different textbooks, but rho more or less is decidedly not the radius of the shaft itself. It is a distance from the center line, and it maxes out at the radius. And usually, people use like R or C as the radius of the shaft. Okay, good questions. Okay, so let's talk about polar moment of inertia. Okay. So as kind of a refresher, we just wrote out that J is equal to the integral of rho squared dA. And rho, as we just discussed, is this distance to it's a distance away from the center line, right? So if we imagine a circle, let's just draw a circle. And let's draw a distance rho. Okay, it's just some spot in that circle. And right now, what I'm gonna do is I'm actually gonna say that this is going to map out an annulus. Like that. You guys know where you folks know where we're going with this? Okay. We want to do an integral, right? We want to do an integral with respect to dA. So, how would you define dA? So here's the question, what is dA? With this drawing that we just made. Yeah?
Is it pi rho squared d rho?
Okay, very close. What's that? Okay. So we're going to do an approximation that this is a very thin, okay, piece. We're going to say that this piece has a width of dr. Okay, now, yes, now is that making it clearer?
Yeah, so pi times rho plus dr squared minus pi rho
Okay, yes. So we're going to do an approximation, though. Okay? We're going to do an approximation that says, what's the perimeter? It's more or less 2 pi rho. Okay? Right? That's the circumference. Perimeter of this thing, or the circumference. It's 2 pi rho, and then I'm going to say times dr. That's the width, and that's going to be the area. Okay? So it's 2 pi rho dr. So now we can substitute this in. So we can substitute in for j. We can say that say j is equal to rho squared, and then dA is 2 pi r dr. Okay, and we're going to do this. We're going to, now that we have a radius, we're going to do it from the middle all the way up to the radius of the shaft, which we're calling C. So then, oops, I wrote it. Sorry, guys. Sorry, everyone. There we go. All right. So what do we have? We have integral of 0 to C of 2 pi rho cubed dr. Okay, and so this will come out to be 2 pi 1/4 rho to the 4th going from 0 to C, and this is pi over 2 C to the 4th. This polar moment of inertia, so now it's a mathematical quantity, but what is it really? It's telling us, if we go back, okay, and we write out tau is equal to torque times rho over j, okay, or tau max is equal to Tc over j, right? What is this telling us? It's telling us that if you have a very large circular cross section, okay, you can put a lot of torque in there and not get much shear stress. Okay, so this is kind of it's how much does it resist the torque that we put in? Okay, that's how we get that's how we get a kind of a feel for what J is. Different shapes will have different polar moment of inertias. Okay, but for this class, more or less what we're dealing with is the polar moment of inertia, or we're dealing with the torsion of shafts that are circular. Okay. So if you have a hollow, let's just say we have a hollow surface, circular shaft, it's not really a surface. What does that look like? That looks something like, that's really bad. Okay, that's too bad. Well, that's not much better. Oh, I should have kept the first one. Anyway, okay, it's at the bottom of the page, which is hard to write. If I have an inner Ci and an outer C naught, okay, the J for this will be pi over 2 C outer to the 4th minus C inner to the 4th. So I'm subtracting away that part that can resist on the inside. And we'll have another term which is called I, and that's going to end up being pi over 4, essentially C to the 4, okay? And the way I try to keep track of these is by saying that that I comes before J in the alphabet, and so I is less than J. So this is the pi over 2 one, the I one is pi over 4, and that's less than the J one. All right. I was optimistic in terms of how much we were able to get done today, all right? And we were trying something a little bit new, and I can go faster. Feel free to send me a message about the pace if this is too slow. we can do something kind of hybrid and go back to what we were doing, but you have enough information to do the in-class questions, and the assignment will come out later today. All right, thank you. Have a wonderful day.
Bro.